Hello, I'm Filip, and I'm from Touchlab, where I work as a senior Kotlin developer. My work is all about improving the developer experience in Kotlin Multiplatform. And I specialize in compilers and build toolchains, more specifically the Kotlin compiler and Gradle. Before we start, to give proper credit, this talk is based on talk done by my colleague, Tadeas Chris, who prepared this talk for DroidCon New York last year. Originally, he was supposed to be here instead of me to give you the talk, but unfortunately, he had to cancel last minute, and he asked me to do the talk instead. I had about 2 days to prepare it. As it turned out, this was enough time for me to change about 70% of the slides. We will see if it's for the better or worse. Let's go on. So the goal of the talk is to give you an overview of what Kotlin Native is and how it works. But before we do that, we need to look at how Native works itself. And the idea is that if you are familiar with JVM or you are an Android developer, there are some similarities and differences, and by comparing those, you will get a better understanding of why Kotlin Native works the way it works. And at the end of the talk, I will give you some best practices for using Kotlin Native or Kotlin Multiplatform in production, or if you're just starting, so what things to do and what things to avoid. So let's start with the compilation itself. Here we have a diagram. We will have many of those today. And this is an example from C, but many native languages work the same way. On the left, we have some source code in the .c files, and we also have header files. And this is the first difference that we will encounter. In C or native languages, it's pretty common to have header files which contain the declarations for our functions, or in some languages, classes. And then the source files have the implementation. Why? Well, it's because in native, the compiler usually sees only a single source file. So we run the compiler for each source file individually, and so that the compiler knows what declarations are provided by some other source files, we have the header files the compiler needs. At the output of the compiler, we get so-called object file. The object file is a binary. It usually contains some assembly code. The binary isn't runnable on its own because, well, these missing pieces that are provided by the other source files aren't there yet. On the other hand, in JVM, things are a little bit simpler. We have regular source code in, like, for example, Kotlin or Java, and we usually compile it by like the whole module at once, right? So the compiler sees the whole module. It compiles it into these .class files, and these are like binaries, but it's just a byte code. It's not a native code, and we like bundle these .class files into a jar. That's not the only thing that differs in terms of compilation. We need to look at build targets. If you are only an Android developer, you might be like, oh, what are build targets? Well, the reason why is that there is a famous saying, compile once, run everywhere. Like that's the whole idea of Java. That doesn't work in native, unfortunately. In native, we need to worry about things like CPU architecture, like ARM versus x64, and the instruction set in all those architectures is completely different. The binary looks very different. We also have platforms, for example. Mostly, this is an operating system thing, right? Like you have Windows, Linux, Mac OS, and so on. And the difference there is that each platform has different calling conventions and maybe system calls. These things usually don't impact how the binary looks like that much, but it's still significant enough so that we need to worry about it. Next, we have build configurations. This is a thing that you might be familiar with from Android, but it's not a thing in JVM itself. Well, the idea is that we have some common presets of compiler flags that change how the compiler works. And you can actually define your own, but these two are like the default that you encounter basically everywhere. Why we have that? Well, the advantage of a debug build is that, as the name suggests, it's debuggable. And it's also faster to build because the compiler skips many important steps, like, for example, the optimizations. As a result, though, it's usually slow in runtime, which is why we can't ship this to customers, because they would complain that the app isn't running as expected. Because of the debugging symbol that we need for the debugging, we also have larger binaries because they take a lot of memory. On the other hand, the release is basically the opposite. We run the optimizations, we don't include debugging symbols. As a result, we get the other benefits. Next, libraries, and this is actually probably the biggest topic here today. Libraries, well, the basic concept is the same in JVM and Native. Like, we want to share our code across multiple projects so that we don't really need to write it everywhere. Let's look at how they are distributed. So first of all, there are multiple options. We have the option of distributing the precompiled binaries plus their headers. Like in JVM world, we would have the jar file. We also have the option of distributing only the source code. And the idea here is that the user will compile the library on their own machine for the targets that they need. And we also have both. And this is actually more common in the JVM world, especially with open source projects. You usually have the precompiled jar, plus you have the source code, so you can like debug it in IDEA or stuff like that. Now, how the libraries influence the compilation? Well, the library, as I mentioned, contains a header file and some binary. The compiler it needs to have only the header file. The binary doesn't influence it at all. And the header file is actually basically the same as we had with the source files. It's just a file full of declarations. What happens with the binary? Well, we will see that a little bit later. For now, let's look at the JVM side first. Here, the library is bundled in a jar, and the jar goes to the compiler. But it also, like, we take the content of the jar and put it in the app jar. The thing is, in JVM, the .class files behave like a header plus the implementation at the same time. So even though the compiler needs the jar, it actually doesn't do anything with it except for compiling the source code that we have. Therefore, there must be something else that takes content of the jar file and puts it in our app jar. Next topic is the dependency management, also very different. In JVM world, or especially Android, we have Gradle. And technically speaking, Gradle is built on top of Maven, and there is also Ivy from Ant, but this is more of a backend thing, and even that is pretty old today. Basically, today you have Gradle, and maybe you know that there is a Maven underneath it. In the native world, it's like in this famous comic, right? There are many standards, sometimes a new pops up. In general, like, you need to know a bunch of these. For iOS development, major one is Swift Package Manager from Apple. That's for Swift. And there is also Cocoa Pods, which was used before. It's much older project and also like used for Apple platforms and package management on that. But many other languages have their own package managers, like you have C, you have Rust, and many more. And the main difference here is that not all package managers have all libraries, not all package managers support all features. So compared to JVM, you will oftentimes need to have multiple package managers if you are dealing with multiple languages. Next, we have library formats. As I've mentioned, on JVM, we have a jar file. That's it. Native, there is a lot, again. We have static and dynamic libraries, and then we have a bunch of different types of frameworks. The static and dynamic libraries are a concept that's universal across many platforms, Windows, Linux, Apple. The frameworks are pure Apple thing, but for iOS especially, we need to be aware of them. So let's look at how they work. And let's start by looking at the jar file first to understand the differences. A jar file is actually just a zip file. It just has a different extension. If you rename it and unzip it, it works as expected. And you get a directory structure that contains a bunch of .class files. Plus, there are some metadata. And optionally, you can also have some resources like images or things that the JVM can load at the runtime. And if you look at the frameworks, on the other hand, well, we see that they are actually very similar. We have the header file in there, and there is the binary in the root called shared in our case. Then there are some metadata, and optionally you can have resources. The header plus the binary is, depending on your definition, a library, and the framework contains the library plus metadata plus resources. So if we assume that .class files are like a header plus binary together, then they are pretty much equivalent, except with a different structure, and except that the framework isn't a zip file, it's just a regular directory. But okay, what about the other types of frameworks? Well, let's look only at the XT framework, which is the newer one and the one that you should use. The problem with native is that you have multiple targets. But the framework or libraries, for that matter, by default, support only one target. So how do you ship some library that supports multiple targets? That's a pretty common thing to do. Well, you have something like an XT framework for rescue. The XT framework is just another directory with predefined structure that contains multiple frameworks, one for each platform that you want to target. That's it. But what about the static and dynamic libraries? Well, let's look at those. A static library, in our case, the extension is .a. That's a convention on Mac or Linux. These conventions are, of course, not universal because there are no standards. And the .a file is an uncompressed archive. It's like a zip file, except without the compression. And inside the archive, you will find a bunch of object files bundled together. This static library becomes eventually part of the executable, which is the main difference from dynamic libraries. Dynamic libraries have on Apple the extension dylib. On Windows, you might be familiar with DLL. And the main difference, as I mentioned, like the static libraries are bundled into the executable directly, whereas dynamic libraries are provided at runtime. They are also final. The compiler or the linker later on does not modify it anymore once the library is produced. And this gives us some interesting trade-offs. The static libraries offer an opportunity for better optimizations during compile time, because the compiler can optimize stuff out and change the library depending on the code that uses it. And most importantly, it can easily drop half of the library if the code doesn't need it, which is often the case. Many times we use libraries and we don't need everything from the library. And because the linking is done at compile time, there is no runtime overhead. The disadvantage is that because the linking is done during compile time, it slows down the compilation process. And technically, we get a larger executable because we need to copy over parts of the library inside the executable. But this is with an asterisk, especially on iOS. If you have dynamic library, you need to include it inside the app bundle. So you may use dynamic libraries. You will technically have lower executable size, but you will not lower your app bundle size, which is what matters, because you will have to put much larger file inside instead. So especially on iOS, you usually get lower total app size with using static libraries. On the other hand, dynamic libraries have the advantage of being independently linkable. Because they are linked at runtime, you can do weird things like hot reloading, or even compile against one version of the library and then provide a different version of the library during runtime without having to recompile your whole app. They are also shared in memory, which is an optimization on the OS, for the OS, because it doesn't have to load multiple versions of the same library in memory. Again, with an asterisk, on iOS, this is true only for system libraries. User libraries or your app libraries don't have this benefit because the app is sandboxed and all the dynamic libraries are loaded for each app individually. The disadvantage is that the linking is done at runtime, therefore it slows the app startup. You will not notice it if you just add one library, but if you overuse this feature and you add like 50, 100 dynamic libraries, which can easily happen if you are not careful, it can it can be noticeable to the user. Like it can easily add a second to the app startup, for example. And the other disadvantage is that you can run into runtime crashes or mostly during startup if you misconfigure your application and your build process, because the compiler will assume that you provide the library to the right place where it must be. And if you don't do that, the application will not start and you will get the famous missing DLL crash. Now we talk about linking of libraries. So what actually is the term linking? Well, linking or a linker is a program that takes the object files plus binaries from libraries and merges them together, fixes all the pointers that are missing in the object files and points them to the right place in the binary. As a result, you get an executable or a dynamic library depending on what you want to build. An important feature is that the linker only, even though it sees dynamic libraries as well, it has to because it needs to know the symbols that the library provides. It actually doesn't copy over much from the dynamic library, only from the static libraries. And for the dynamic libraries, all it does is that it modifies the executable header and puts a mention that this library is expected to be loaded at a runtime. Okay, we have an executable. So what we can do, we can start our program finally. So let's compare. On the JVM, we have a jar. We can start a JVM, and we just run it. On the native side, we have a binary. We just run it. Oh, wait, we still need to deal with the dynamic libraries. Fortunately, for us, this is mostly solved by the operating system. In the case of Apple platforms, there is a process called DYLD, which stands for Dynamic Linker. And this process, what it does is that during startup, it looks at the executable header, it sees all the dynamic libraries that it needs to find, and it goes searching for them. There are predefined places where it will search, it's like a path that you have in shell, right? Like you run a command and the shell will look for binary in a specific place. This is the same thing with the dynamic linking, except the path is different. So assuming that you put your library in the right place, the dynamic linker will pick it up, load it into memory, and it will perform the dynamic linking in memory without modifying the executable. And now is a good time to admit that I've oversimplified the situation on the JVM side a little bit, because technically speaking, you can achieve very similar thing with JVM. You see, you don't need to copy over the content of a jar from a library into your app jar. Doing so is actually not the default, and if you do that, you create a thing called a fed jar. In JVM, you oftentimes can do the fact that you just provide the jar file to the JVM as well. And the JVM will load the content of the jar file, it will unzip it, and read all the .class files and link those dynamically in runtime as well. And because by building the fed jar, we are just copying over the class files, well, there is no static linking, right? So we can come to the conclusion that in JVM, there is no static linking and there is only dynamic linking. But the similarities here and the trade-offs are very similar. Okay, so we've covered the main features of native development and from the point of view of building applications. Now we can look at how the Kotlin Native works from this perspective. This diagram may look a little bit overwhelming, but it's actually relatively simple if we apply all the concepts that we've seen so far. On the left side, we have source files. On the top, there are Kotlin modules, and on the bottom, we have a Swift file with a Swift module. In Kotlin Native, we first need to compile our Kotlin code. For that, we invoke the Kotlin compiler individually for each of our modules. The Kotlin compiler produces a file called klib. This file is like the jar file that we've seen before, except it doesn't contain the .class files. It contains a serialized form of the intermediate representation of the Kotlin language, which is used by the Kotlin compiler. The point of these klibs is that you can distribute your libraries as these klibs. They are pre-compiled in that way. And because this isn't a machine code, you can't just run it easily. It's used by the Kotlin compiler later on to actually create a binary for the native target. And for that, we have something that's called Kotlin linker. And in fact, this Kotlin linker is just the Kotlin compiler run with a different set of flags. In Gradle, you usually see tasks called link ARM64 or link iOS ARM64, something like that. And all this task does is that it invokes this Kotlin compiler with the specific flags to produce the binary. This linker takes as an input all Kotlin klibs that the program will consist of, including third-party libraries. It loads them into memory, unzips them, deserializes the IR. It reconstructs, therefore, the whole program inside memory. Then it uses LLVM to emit binary. And depending on your configuration, in our case, we chosen framework, it outputs the native type of binary that you asked for. In our case, we chose framework basically because this is the way we integrate Kotlin in Swift. And this is what you will be using most of the time if you are targeting iOS. The framework can be static or dynamic. That's your choice. You can just configure the compiler to do so. And this framework is, from the Swift point of view, just an Objective-C framework. Right? There is pretty much no difference. And as such, the framework contains a header file and a binary, as we've seen before. This header file then goes to the Swift compiler. It needs it in order to compile the Swift code, which can depend on the Kotlin code. Swift compiler outputs an object file for the Swift. And we can use this object file to give it to the linker. We also take the binary from the framework. The linker is happy, and we get an executable that combines Swift and Kotlin. Now there is a good point in time to mention that from this diagram, you can see that there is only a single Kotlin framework. You can technically create more than one. However, because they will be produced independently, these two will be incompatible with each other. Therefore, you will not be able to call Kotlin code from one framework to the other framework. And I strictly advise against doing that because the framework contains a lot of things, like, for example, the Kotlin standard library and a bunch of other stuff. So like, you are putting a lot of extra code into your binary, thus increasing it significantly. If you can avoid this problem basically at any cost, don't do that. There are certain use cases where you have to, but try to avoid them as much as possible, basically. The second important thing about Kotlin Native is how the Kotlin to Swift interrupts work. So as of the moment, there is no direct Kotlin to Swift interrupt. They can't talk to each other at all. Instead, there is a middleman called Objective-C, and both Kotlin and Swift have a pretty good interop with Objective-C. Unfortunately, that doesn't mean there is a good interop between Kotlin and Swift. Objective-C is a pretty old language. As we will see, this creates some problems. I will mention those later, but I basically expect that many of the modern features that we are used to from Kotlin and Swift don't exist in Objective-C and therefore are lost during the translation process. Now let's look at some best practices. If you are starting, I would really recommend to try iOS or some native development first, right? Like create a project, play with it, run into issues, fix them, get familiar with the platform enough that you know how to configure the projects, and then add KMP. You will have much better time, trust me, because if you try to use KMP first, you will have to deal with all those issues at once, and that's not fun. Second, if you are trying to adopt KMP in teams or companies, and especially large teams, be aware that the issue is always about people and not the technology. Convincing, especially the iOS developers, to use KMP is oftentimes the biggest challenge, and if you can't convince them, oftentimes you are not going to succeed. Just keeping that in mind. And to completely disregard my previous advice, from now on I will just focus on the technology because that's much simpler. So the first issue that many companies run into with Kotlin Native is the build time. And it's true that the Kotlin compiler can take a while to create a library or the framework, but things are improving quite quickly, and there are a few things that we can do about it. So first of all, you should only build targets that you need. Right? For example, if you are developing an application and you are running it in a simulator, you don't need the executable for real iOS. If you run your tests on macOS, you again don't need a binary for the iOS side. If you misconfigure your build and build all the targets at once, you are multiplying your build time because you have to build each binary from scratch, basically. And this is a common issue that we see over and over again, especially in CI, for example. Second, you should give Gradle more RAM, or more specifically, you should give the Kotlin native linker more RAM. The sad reality is that the Kotlin compiler isn't the most optimized piece of software in the world, and as such, it really likes memory, and unless you want your build to spend half of the time garbage collecting, it's a really good idea to increase the memory limit. For context, like a medium-sized project could easily need like 10 gigs plus, like depending on what it's doing. And a third important thing is to limit the exported declarations. And by exported declarations, I mean the declarations that are visible from Kotlin in Swift. Right? The Kotlin compiler needs to create wrappers in Objective-C for each declaration that is callable from Swift. That's extra code, that's extra classes, stuff like that. So if you export the whole project, the compiler will have to generate wrappers for every single declaration. That means doubling your project size. That impacts compilation time, but also binary size. So what you will find in many projects is that they just export all the libraries because at occasion they needed some type from the library. It's better to not export the libraries and instead figure out how to convince the compiler to export the type you need for you. For example, if you include the type in a function that is exported, it will automatically load all the transitive dependencies of that function, and therefore you will get your type that you want without having to export everything. And the truth is that in Swift, you very rarely need to access all of the Kotlin code. Usually you have just one layer that talks to Swift, and this usually is like 20% of the application or even less. Last but not least, well, definitely not least, measure. If you are optimizing anything, especially compilers, measure what you are doing and how it impacts the desired results. Optimizing is difficult, and this is, again, especially true with compilers which are complex and sometimes behave in a weird way. And also, keep in mind that the compiler is a JVM process. Therefore, all the fun things like the JIT messing with your measuring comes into play. Another important point is, and many JVM developers aren't used to this, warnings in the native world are usually more serious than in JVM. So be sure to, ideally you should have 0 warnings, but you should read your warnings, understand them, and fix them, especially those from the linker. They oftentimes point to serious issues, and if you don't understand what the warning means, learn what the warning means, or otherwise assume it's very bad. And yeah, not doing so will oftentimes lead to weird issues that may not be apparent at first. Unfortunately, the warnings also aren't always that descriptive. So the warning will just tell you there is an error or there is some problem. You oftentimes don't know what the problem is. Now, we get to the issue with the Objective-C interop. Well, as I've hinted at, many of the Kotlin features are not well supported. To give you an example of that, right? For example, sealed classes, they become just classes, so you can't switch over them in Swift. We also have enums. You can switch over those in Swift, but they are not exhaustible. So you have to have a default case in every of your switch. iOS developers will not be happy about that. You also don't have any default arguments. So if you have an API, that is based about immutability and data classes, and you rely on a copy method to create new objects from those data classes, keep in mind that on the iOS side, the copy method requires all the parameters to be provided. Not a good experience. We also don't have any generics for interfaces and functions. We have some generics for classes at least. And there is more issues like that, like for example, flows. They are not really easily callable from Swift because they have async sequences. Suspend functions, well, they technically work, but you usually end up like with issues with cancellation and stuff like that. And so on. The list goes like this is not even like an exhaustive list of all the issues. So what to do with that? Many things. Like second of all, you should consider how your Kotlin code looks in Swift and adjust your API accordingly. You should understand the limitations and ideally try to consume your Kotlin code from Swift so that you understand the pain of the other people. And first of all, like the important thing is that you should use Sky from Touchlab because that's a compiler plugin which significantly improves the interop. Not everything is supported, not everything can be supported, but you will be surprised how much easier your life will be with it. Speaking of Touchlab, we improve the KMP developer experience for our clients, but also for our community. As such, we have many open source resources. I've already mentioned Sky, but we also have CamKit, for example, which is a Git template that you can download and like play with KMP pre-configured. Just keep in mind that the ecosystem is evolving quite quickly, and we are not always up to date with updating all the dependencies. So you might want to like increase the versions in there. We also have Cambridge, which solves the problem in larger teams where they have 2 teams, one for Android and one for iOS. They oftentimes don't even have a common repo because why would they? They develop different applications so far. And then getting the Kotlin framework from Android developers, which usually write the shared code, to the iOS side is oftentimes logistically very challenging. So Cambridge somewhat solves that. And there are many more of these. We, for example, have a blog where we post about Kotlin Multiplatform quite frequently, and we share like even the best practices that we learn on the way. And we are also like to talk to the community and like collect feedback on things we do or how the Kotlin Multiplatform works. So if you like use Kotlin Multiplatform and like you want to chat like about the technology or have some issues, like we are looking for things that we can solve basically. And that includes like either paid work or like open source work, depending on like what the thing is. So yeah, so definitely check it out. And that brings me to the end of the presentation. Today we've discussed how the JVM and native world compares in terms of the build process. We look at things like the compilation, the differences in headers, binaries. We talked about libraries, how the distribution works there, what are static and dynamic libraries, why are they important. And on the way, we've learned how to build an executable from the compiler point of view. Then we look at the basics of Kotlin Native for iOS and like some of the key features of it. And at the end, we discuss some best practices for using Kotlin Native. That's all from me. Thank you, and keep in mind to use Sky. It's like the only thing that I want to bring from this presentation, basically. Thank you.
Yeah, thank you. So we have 2 questions. The first one is how to distribute separate Kotlin modules for iOS if we can't include multiple frameworks with that Kotlin framework.
Yeah, so that's a limitation that we currently have. You can have different modules, but you need to like include them in your linker, right? Like the Kotlin linker. So ideally set up your build such that the framework is built at the last moment on the iOS side, and that way you can like point to the different modules that you need and build it like as part of the build process for iOS. Like that's the simplest thing to do. And other than that, like if you really like, there is no other way around it. For example, you have an SDK from some vendor. Well, maybe you will have to include the framework. And, like there's not much that we can do about it right now.
Okay, thank you. More questions arrived actually in the last minute. Can we use Kotlin Native for RP2040, for example, Raspberry Pi?
Yeah, so I'm not 100% sure on this, but I know that things like that were possible in the past, but unfortunately the Kotlin Native team decided to deprecate some of the native targets, especially on Linux, and those were like the older ARM architectures. So I know that not all ARM architectures are currently supported, but some are. So depending on the version of ARM that these two platforms use, it may or may not be possible.
Thank you. Why can't I build executable for macOS or iOS on Windows?
Yeah, that's my favorite question. Well, thanks Apple, right? Like that's pretty much like the tool chain for building Apple platforms is available only on Apple. That's nothing that JetBrains can do about this.
How do you see the future of KMP when Compose Multiplatform matures to production ready?
I think like Compose Multiplatform like uses KMP under the hood, right? Like that's just an like building block on top of it, basically. And the great advantage of like Compose Multiplatform is that you can choose which parts of the UI you write natively and which parts you write in Compose Multiplatform. Depending on your needs and your project, you might lean more in Compose Multiplatform and therefore not have to deal with the Objective-C interop right now. But the whole build process that we've covered here is the same. And therefore, I think that Compose Multiplatform like will leverage this quite well. And then there is a great potential for it to like be the next major way how to write applications, right? Like we have Flutter and things like that. The Compose Multiplatform might be the next thing, or an alternative at least.
Thank you. And the last question, is there a way to include Kotlin Native on Android?
Well, technically, yes, though I'm not sure if that's something you would necessarily want to do, right? Like because Kotlin Native, you can compile it into a C library. That's just fine. There is a C interop, and that way you could like call the C library from your JVM using JNI. Though I'm not sure like what are the advantages of there, because like Kotlin is just JVM, so compiling directly to JVM is usually just much simpler.
Okay, thank you. So that's all about questions. If you have more questions, of course, you can catch Filip outside of the room at the speakers table. Thank you very much, Filip.